Section: Contents. In this section, we address the growing security concerns associated with advanced large language models, LLMs. As these models evolve, developers like Google DeepMind and Anthropic have expressed worries about their potential misuse, particularly in creating harmful technologies. For instance, Google noted that future updates could enhance the model's capabilities in dangerous ways, while Anthropic activated safety protocols due to concerns about assisting in the creation of weapons. Currently, many leading LLMs are available through closed systems, but we are seeing a rise in open-weight models, which are released more frequently and are only slightly behind closed models in terms of capabilities. Open models provide advantages like transparency and reduced power concentration, but they also pose risks due to potential misuse and modifications by others. This raises the question of how we can effectively reduce harmful applications of these open-weight models. The field of open-weight model safety is still developing. Closed models keep their weights secure, allowing for better monitoring, while open models can be altered freely, making them more vulnerable. Although there have been efforts to create tamper-resistant models, these methods can often be reversed with minimal adjustments. In our research, we explore whether we can enhance the tamper resistance of open-weight models by filtering out harmful content from their training data. We aim to ensure that these models do not learn about biothreats during training, which we believe will make it harder for attackers to exploit them. Our contributions include: 1. Knowledge prevention. We present an efficient data filtering process that uses less than 1% of total training resources. This method effectively prevents the acquisition of biothreat knowledge without harming unrelated skills. 2. Tamper resistance. Our findings show that this filtering can significantly improve tamper resistance, outperforming existing methods when faced with adversarial fine-tuning. 3. Defense in depth. We acknowledge that while filtering helps, it cannot stop LLMs from using harmful knowledge provided in context. We also explore additional defense techniques, though we find that none are fully resistant to combined attack strategies. 4. Model Suite. We are releasing a set of language models with 6.9 billion parameters that incorporate our filtering and post-training safeguards. These models will help researchers understand how removing certain training data affects model behavior. Additionally, we examine the challenges of evaluating LLM safeguards, introduce a new hybrid unlearning algorithm, and share our experiences with synthetic document training. Although our focus isn't on machine unlearning, our models can serve as a platform for studying these algorithms. We hope our findings will aid in developing effective risk management strategies for open-weight models. In our investigation, we also consider whether we can prevent LLMs from acquiring unwanted knowledge through careful data curation. By removing documents flagged for containing harmful information, we aim to create models that lack this knowledge while maintaining their general understanding. We implement a multi-stage filtering process to identify and exclude these documents, training models on both the original and filtered datasets. Our goal is to demonstrate that filtered models possess significantly less harmful knowledge without sacrificing their overall capabilities. While we focus on biothreats, our approach can be adapted to other areas as well. Section Summary. In this section, we explore the potential of data filtering to prevent large language models, LLMs, from acquiring undesirable knowledge, specifically regarding biothreats, by implementing a multi-stage filtering pipeline. Our approach aims to ensure that filtered models retain general knowledge while significantly reducing proxy biothreat capabilities, thereby enhancing their safety against harmful uses. Section: Multi-stage filtering. In this section, we outline our method for filtering training data to identify and remove documents related to biothreat proxy knowledge. This task is challenging due to the vast number of documents in modern pre-training datasets, which can exceed hundreds of millions. Our approach involves a multi-stage filtering process, starting with a keyword block list and escalating to a modern BERT classifier if 2 or more keywords are detected in a document. In the first stage, we utilize Llama 3.370b to create lists of key terms from the WMDP BioForget dataset, which contains over 24,000 documents. We check each document in our training dataset for the presence of 2 or more blocklist terms. If a document has fewer than 2 terms, we take no further action, which applies to about 91.58% of pre-training documents. Documents with blocked terms move on to the next stage. This initial filtering is efficient and can be easily parallelized. In the second stage, we employ a modern BERT classifier, which we fine-tuned using expert-labeled proxy documents and general biology texts, totaling around 198,184 documents. This classifier reviews the documents that passed the first stage. Because of its small size and the limited number of documents it processes, this filtering stage uses only a tiny fraction of the computational resources compared to model training. We can adjust the number of filtering stages based on the training data. For instance, if we want a stricter filter, we can skip the modern BERT stage, filtering out all documents with blocked terms directly. Conversely, we can add more escalation stages to enhance precision. Our training approach involves training models on a large dataset of 500 billion tokens, followed by a 50 billion token phase with more specific data. We do not focus on formal instruction fine-tuning since our goal is to evaluate single-turn question answering rather than creating conversational agents. We train several decoder-only transformers with 6.9 billion parameters, similar in structure to Pythia 6.9b. Models trained on filtered datasets undergo slightly more than 1 epoch to match the training token count of the baseline model. Our models aim for 50% accuracy on the WMDP bio benchmark, and we allocate our remaining resources to filtering experiments. We implement 2 filtering strategies, a strong filter and a weak filter. The strong filter uses a single-stage blocklist during both pre-training and annealing, filtering out 8.42% of pre-training documents. The weak filter maintains the same pre-training filtering but uses a 2-stage process for annealing, resulting in 4.96% of those documents being filtered. We replace filtered documents with those approved by the modern BERT classifier to keep a similar amount of scientific data. We also explore circuit breaking, CB, and latent adversarial training, LAT. CB involves training low-rank adapters at various network layers to preserve benign data while scrambling harmful data. We have found CB effective in suppressing unwanted knowledge. With CB plus LAT, we fine-tune models under hidden activation perturbations to counteract unwanted behaviors, which has shown to improve resistance to certain attacks. Overall, we find that both CB and CB plus LAT perform similarly, with CB plus LAT offering stronger resistance to some input space attacks. Section Summary. In this section, we outline our multi-stage filtering approach to remove documents related to biothreat proxy knowledge from our training dataset, starting with a keyword blocklist filter followed by a modern BERT classifier for documents that contain multiple blocked terms. We also discuss our training methodology, which includes strong and weak filtering strategies, and the implementation of circuit breaking and latent adversarial training to enhance model robustness against harmful knowledge. Section WMDP Bio. In this section, we focus on biological knowledge that can indicate information relevant to bio risk. To assess this knowledge, we use WMDP Bio, a public benchmark consisting of multiple-choice questions created by experts. This benchmark evaluates harmless knowledge related to biothreats and dual-use biological processes. It is commonly used to test the safeguards of large language models, LLMs. The WMDP Bio evaluation includes questions from 6 important topics, which we will outline along with example questions. However, it's important to note that WMDP Bio does not directly assess an LLM's ability to handle bio risk, as that may require more complex skills like reasoning across different types of data. Instead, it measures factual knowledge related to bio risk topics. Other studies have used more complex evaluations and exercises to assess bio risk knowledge, but we find that the multiple-choice format, despite its limitations, offers a standardized way to evaluate the internalized knowledge of our base models. Our aim is to gauge an LLM's true understanding of biothreats rather than its ability to guess answers using shortcuts. Previous research has shown that LLMs can perform well on multiple-choice questions by using heuristics, even when given only answer choices without the original questions. We found that the WMDP bioevaluation can be manipulated. For instance, choosing the longest answer can yield a 46% accuracy rate. To address this, we evaluate curated subsets of WMDP bio to reduce the influence of these shortcuts. We have two specific subsets: WMDP bio-robust MCQA, which excludes samples where other LLMs guessed correctly based solely on answer choices, and WMDP bio-verified close, which assesses answers without providing all choices, making it a tougher evaluation. Additionally, we test knowledge under two types of input space adversarial attacks. We conduct each attack 3 times and report the average results. The first attack, few-shot, uses 16 held-out question-answer pairs. The second, universal greedy coordinate gradient, is a more advanced attack that requires access to the model's tokenizer and outputs. We optimize a universal adversarial prefix to elicit correct answers across a set of 32 held-out pairs. To measure general capabilities, we use standard question answering benchmarks to ensure that knowledge unrelated to undesired behaviors remains intact. We utilize the Language Model Evaluation Harness and focus on MMLU, which covers a wide range of topics. We report performance on two subsets: MMLU No Bio, which excludes biology-related topics, and MMLU HSC Bio, which includes high school and college biology but excludes virology and medical genomics due to overlap with WMDP Bio. We also use PIQA to evaluate physical common sense reasoning through multiple-choice questions about everyday interactions, and Lambda to test text comprehension by asking models to predict the last word of a passage, which requires understanding the entire context. Section Summary. In this section, we introduce WMDP Bio, a benchmark designed to assess knowledge of biothreat-related biological processes through multiple-choice questions, while ensuring that evaluations focus on genuine understanding rather than heuristic guessing. We also discuss our methods for mitigating shortcut exploitation and measuring general capabilities using various question-answering benchmarks to ensure that safeguards do not compromise unrelated knowledge. Section: Hella Swag Zellers 2019 Hella Swag CA. In this section, we evaluate common-sense natural language inference using the Hella Swag dataset, which challenges models to choose plausible endings for everyday scenarios. To succeed, we must differentiate between seemingly reasonable but nonsensical completions and genuinely coherent ones. We implement training data filtering to maintain general knowledge while reducing unwanted biothreat knowledge. Our findings indicate that this filtering significantly limits the acquisition of biothreat knowledge during training, especially excelling with close-style prompts. In multiple-choice tests, filtering performs better than the baseline but not as well as certain contrastive techniques. However, we will later demonstrate that filtering and these techniques can work well together. Importantly, these enhancements come with minimal costs and do not negatively impact non-biological capabilities. We also find that training data filtering enhances our model's resilience against input space attacks. To assess this robustness, we test against few-shot and GCGU attacks. The results show that filtering generally outperforms contrastive methods during GCGU attacks, while it does better than the baseline but not as well as contrastive methods in few-shot attacks. The key takeaway from these evaluations is that training data filtering effectively reduces unwanted knowledge in large language models, LLMs. By carefully curating pre-training data, we can achieve significant safety improvements. In the next section, we will illustrate how data filtering provides a strong defense against adversarial fine-tuning. Next, we assess the tamper-resistance of our filtered models against various tampering threats, including latent space attacks, adversarial fine-tuning, and benign fine-tuning. For latent space attacks, we create prompt perturbations at specific layers and optimize them to ensure correct responses on a set of questions. We use a specific number of optimization steps and a learning rate, adjusting parameters to achieve the best results. In our adversarial fine-tuning tests, we fine-tune models on a specific dataset for a set number of epochs, using a defined batch size and context window. We also experimented with mixing benign data into our training but found it did not enhance performance, so we focused on the original dataset. For benign fine-tuning, we fine-tune models similarly to our adversarial approach but use a different dataset. This tests the models against non-adversarial tampering, which can undermine LLM safeguards without needing access to specialized data. Our results show that pre-training data filtering provides excellent resistance to tampering. In our attack comparisons, filtered models are the most resilient, except in one case where latent space attacks were unexpectedly effective in multiple-choice settings. We suspect this is due to the model developing useful strategies for answering those questions. Later, we will show that combining pre-training data filtering with contrastive techniques enhances our safeguards. Finally, we confirm that our filtered models maintain their performance against benign fine-tuning, unlike other methods that are vulnerable to such interventions. Section Summary. In this section, we evaluate the effectiveness of training data filtering in enhancing common-sense natural language inference and mitigating unwanted knowledge in language models. Our findings indicate that filtering improves robustness against various attacks, including tampering threats, while maintaining performance on non-bio capabilities, suggesting it is a strong defense mechanism for model safety. Section. Our filtered models appear to be resistant to greater amounts of adversarial fine-tuning than related works have tested. In this section, we observe that our filtered models seem to withstand more adversarial fine-tuning than what has been tested in related studies. Although comparing fine-tuning attack setups is challenging, we analyze details from previous works on adversarial fine-tuning attacks on language models with over 1 billion parameters. We conduct fine-tuning attacks using the highest number of unique examples, total steps, and the product of steps and batch size compared to these studies. We adopt a defense in-depth approach, which involves using multiple layers of safeguards to reduce risks, a common practice in safety-critical environments. Previous research has shown that combining different defense strategies can create beneficial synergies. We previously utilized circuit breaking, CB, and circuit breaking plus LAT, CB plus LAT, as post-training baselines, but these methods can work alongside training data filtering. We emphasize that CB can enhance data filtering in two significant ways. Regarding retrieval augmentation attacks, we note that large language models, LLMs, do not need to possess harmful information to provide it. For instance, AI agents often have tools that enable them to search the web for information. However, studies indicate that these agents can create safety issues, as LLMs may not behave safely when using retrieval tools. Consequently, when harmful information is easily accessible, retrieval augmentation can undermine the effectiveness of training data filtering. While data filtering cannot stop harmful information from being retrieved in context, circuit breaking can. To assess model safety with retrieval augmentation, we created a benchmark with 1,000 multiple-choice questions related to biothreats, using two evaluation modes, closed book and open book. We prompted Claude 3.7 Sonnet to generate questions based on biology paper abstracts, ensuring that the questions had one correct answer known to experts, were difficult for non-experts without context, and were easy for non-experts with the abstract. Our results show that filtered models perform well in the open book evaluation, but those with CB and CB plus LAT struggle to answer biology questions correctly, even when the answers are provided in context. However, we found that no models could resist an ensemble fine-tuning plus open book attack, indicating a potential vulnerability in this defense in-depth strategy. We then evaluated whether applying circuit breaking to our filtered models enhances their resistance to attacks compared to using either method alone. Our findings indicate that models with combined defenses show increased resistance to few-shot and latent space attacks, while maintaining comparable performance in other evaluations. This suggests that integrating both filtering and CB may improve defense against various attacks. Lastly, we found that training on our synthetic biothreat misinformation documents did not significantly reduce biothreat proxy capabilities. Although we observed that models trained on these documents were slightly slower to learn biothreat knowledge during fine-tuning attacks, we found no strong evidence that mixing these documents with training data was more effective than filtering alone. In fact, fine-tuning on these documents often increased the model's biothreat knowledge. This was unexpected, especially given previous successful concepts. We speculate that our synthetic datasets may have been sufficient to help the model grasp biology concepts, allowing it to leverage heuristics in our evaluations. We also suspect that the way we generated synthetic documents may not have effectively instilled coherent incorrect beliefs in the LLMs. Therefore, we conclude that incorporating incorrect information into LLMs through synthetic document training is complex and may require carefully designed datasets for future work. Section Summary. In this section, we demonstrate that our filtered models exhibit greater resistance to adversarial fine-tuning than previous works, and we highlight the complementary benefits of combining data filtering with circuit breaking to enhance model safety against various attack types. Additionally, we find that training on synthetic misinformation documents does not effectively suppress biothreat proxy knowledge, suggesting that creating coherent incorrect information for LLMs is challenging and requires careful dataset design. Section: Data Filtering and Curation. In this section, we discuss the importance of filtering harmful content from training data as a crucial risk management strategy. However, curating large datasets from the web is challenging due to high costs, potential filtering errors, and the complex nature of internet text, which includes various languages and cultural biases. We note that modern datasets used for training large language models, LLMs, often contain harmful content. While some developers are attempting to filter this harmful content, they have not provided clear details on their methods or the effectiveness of their filtering. We also highlight that other studies have explored the effects of filtering pre-training data on safety in language models, particularly those with billions of parameters. Some have used model distillation on filtered data to suppress harmful capabilities, but their experiments were limited to smaller models. In our work, we demonstrate effective capability suppression through pre-training data filtering on larger models. We examine methods for unlearning harmful capabilities in LLMs, including fine-tuning and various machine unlearning techniques. Despite recent advancements, these methods face challenges such as vulnerability to attacks and side effects. We address the issue of prompt-based attacks that can reveal harmful behaviors in LLMs, even when they are designed to avoid such outputs. Our findings indicate that filtering pre-training data enhances resistance to these types of attacks. Additionally, we explore white box techniques that target LLMs to elicit harmful capabilities. Previous research has shown that few-shot fine-tuning attacks are particularly effective, and we achieve strong tamper resistance through our data filtering approach. We define safety cases as structured arguments that justify the acceptable risk level of a system. We believe that developing safety cases is essential for managing risks associated with advanced AI systems. Our research contributes to understanding how to create safety cases based on a model's resistance to tampering. We recognize the ongoing challenges in building durable safeguards for LLMs, particularly in the context of open-weight models. By focusing on pre-training interventions, we demonstrate significant improvements in tamper resistance. Our results suggest that data filtering is a valuable component of risk management for open-weight models, although comprehensive strategies are needed due to external factors influencing risk. Finally, while our primary focus has been on open-weight models, we acknowledge that data filtering can also benefit closed-weight models by enhancing their robustness against attacks. Section Summary. In this section, we discuss the challenges of filtering harmful content from training data for language models, highlighting the difficulties in curation, the presence of harmful content in modern datasets, and the limitations of existing machine unlearning techniques. We also emphasize the importance of pre-training data filtering as a robust risk management strategy for both open-weight and closed-weight models, while acknowledging the need for ongoing risk monitoring and mitigation efforts. Section: What is different about filtering biothreat proxy text versus filtering for toxic or generically "harmful" text? In this section, we explore the differences between filtering biothreat proxy text and filtering for toxic or generally harmful text. We have found that filtering biothreat proxy text from training data for language models can lead to models that are safe from biological threats and resistant to tampering. Our findings align with previous work that distilled models with fewer than 500 million parameters. However, these results seem to contradict recent studies where researchers trained language models on data filtered for toxic and harmful content. Those studies indicated that their safety-tuned models were sometimes less robust against certain attacks compared to unfiltered models. In our experiments, we tested various defenses and attacks on models, building on previous findings. We showed that filtered models do not consistently resist fine-tuning attacks better than unfiltered ones and are also vulnerable to few-shot prompting attacks. We revisited the hypothesis that harmful training data might lead to safer models, suggesting that language models may need to understand harmful behaviors to resist them effectively. While this hypothesis proposes that safety is not about censorship, and bad data may lead to good models, it does not fully explain our successful results. We speculate that this hypothesis applies mainly to emergent behaviors, like toxicity, which do not require precise knowledge. However, we believe it does not apply to specific knowledge, such as scientific facts, which come from a limited set of training documents. To suppress unwanted knowledge, we propose that filtering pre-training data can create strong safeguards in language models. Future research on training data curation could enhance our understanding of safeguards. Our experiments are limited to a specific set of unimodel language models with 6.9 billion parameters, without instruction fine-tuning. Due to logistical and financial constraints, we trained these models on 550 billion tokens until they achieved over 50% performance on the WMDP bioevaluation. They do not compete well with other open language models of similar sizes. We focused solely on biothreat proxy knowledge, and while we aim to strengthen our attacks, our evaluation methods can only provide a lower bound for the worst-case behavior. Other tampering attacks might be more effective than those we implemented. In real-world applications, it is crucial to define clear boundaries for acceptable model behavior. However, this often leads to gray areas related to dual-use capabilities and the context of harm. We chose to use performance on the existing WMDP bio benchmark as our target without addressing this challenge directly. As we discussed, training data filtering has limitations, as it cannot defend against retrieval augmentation attacks and may not sufficiently suppress harmful tendencies like generating toxic text. These issues emphasize the importance of using multiple defenses to reduce risks. Additionally, our filters remove a significant amount of training data, which could unpredictably affect model behavior beyond standard benchmarks. We believe that improving our filters' classification performance is a manageable engineering challenge and not a fundamental flaw in data filtering. This work aims to support the development of methods and standards for managing risks associated with open-weight language models. We anticipate primarily positive impacts from our research. While we focus on biothreat proxy knowledge, we only use existing datasets and benchmarks and do not introduce new attacks. The models we release have limited capabilities compared to existing open-weight models, and we have chosen not to release our dataset of filtered pre-training data out of caution. Given the limitations of our models, we believe that training larger, more capable, or multimodal models for data filtering will be beneficial for ongoing research on open-weight safeguards. Such models could help us understand how data filtering applies to models of varying scales, potentially allowing practitioners to estimate how well filtering techniques generalize to more advanced models. Section Summary. In this section, we explore the differences in filtering biothreat proxy text compared to toxic or harmful text, finding that while filtering can yield bio-benign models, it does not consistently enhance resistance to attacks and may even remove valuable training data. We also highlight the need for precise definitions of acceptable model behavior and suggest that future research should focus on improving data filtering techniques to better manage risks associated with open-weight language models. Section. What does ignorance look like, mechanistically? In this section, we explore what ignorance looks like on a mechanistic level. Our work on filtering training data helps us understand that techniques used after training often do not effectively eliminate the neural pathways that hold unwanted knowledge in large language models, LLMs. So far, there has been limited research on the neural mechanisms that differentiate deep ignorance from shallow ignorance in LLMs. We believe that the models we have made publicly available can be valuable for research focused on interpretability. Regarding comprehensive defense strategies, we recognize that managing risks associated with open-weight LLMs may require a variety of approaches to monitor and reduce these risks. Our findings indicate that data filtering and circuit breaking techniques are essential components of a risk management strategy for open-weight LLMs. However, we also see the potential for additional methods to enhance risk management in this area. Future research aimed at developing techniques and establishing standards for managing risks in open-weight models will be beneficial. We would like to express our gratitude to several individuals for their insightful discussions, including Yijin Choi, Liwei Zhang, and many others. We also appreciate the methodological contributions from Alex Roby and Alexandra Soli. Jay Patel helped coordinate our collaboration, while Ayman Syed provided support for our computational needs during experiments. Kyle O'Brien received financial support from the Cambridge Era AI Fellowship. We are thankful to CoreWeave for their GPU donations, which facilitated our research, and to Prime Intellect for their prompt assistance with hardware issues. Lastly, we acknowledge GW4 and the UL Met Office for maintaining the assembled compute cluster, which was crucial for our experiments.